polynomials, we're going to start graphing them. What we just got done doing is finding the zeros, and that's really important for graphing because what are the zeros on your graph?
Where they cross.
Where it crosses the x-axis. Okay, so now we're going to talk about a couple other important pieces. The first thing I have on here is kind of the first place we started with the last section, but I just want to throw this out there a couple different times. So the way a polynomial is written, we had this weird looking definition, a sub n, x to the n, a sub n minus 1, x to the n minus 1. Do you guys remember writing this down before?
Mm-hmm.
Okay, so that's a polynomial. When I look at that, what is the degree? In general, what is the degree of a polynomial? The highest exponent. So if it's written like this, it would be that n. It doesn't have to be the first one. So we should double check and find that highest power. The coefficients. What are coefficients?
The number
The number in front. If I said like 3x squared, what's the coefficient? 3. So it's these a's. The a sub n minus 1, and so on. In front of our variable. What's the constant? The one without a variable. In this case, it's that a sub 0. Leading coefficient. What's that in my scenario up here? The first, that a sub n. It's just the coefficient of the term with the highest power. It doesn't have to necessarily be the first one. A lot of times it is, but you find where the highest power is. The number in front of that is the leading coefficient. And the leading term is that whole term, the coefficient and the x. The thing about a polynomial, when you are looking at it, all the exponents have to be whole numbers. So that means you won't see any negative exponents, no fractions or decimals in your exponents. All those powers of x have to be like 1, 2, 3, 4, and so on. When you're looking at the graph, it's always going to be a nice smooth curve. There's no breaks in the graph, there's no corners like you see in an absolute value. It's just a curve that keeps going forever. We can use transformations sometimes. Any of the transformation rules we have still work with these. So the first thing I wanted to do is just practice looking at an expression and deciding if it is a polynomial. So if I look at A, would that one be a polynomial? Yeah. All right. What is the degree? 4. The highest power is 4. It doesn't have to be the first one. All right. B, a square root. A square root is like what power? The 1/2. Is that a polynomial? No. In a polynomial, you can't have a fraction in the exponent. see. Is this one going to be a polynomial? No. When you're dividing by x, that is kind of like a negative exponent. So this one is not because you have a variable in the denominator. You can't be dividing by x in a polynomial. Is this one a polynomial? Yeah, that one would work. The degree though. I think I mentioned this in the last section. 0, isn't that the same as 0x or 0x squared or 0x cubed? So could you give me just a single degree? No. So there is no degree if it's just equal to 0, because you could put any power of x with it. All right, is e a polynomial? Yes. Okay, the degree. This one is different because 8 is only the same thing as 8 times x to what power? 0. Because 8 is not the same as 8x. But what does x to the 0 power turn into? A 1. So this is a degree of 0. Degree is essentially saying how many variables are there. If it's just a plain 8, there are no variables. So the degree is 0. All right, is this one a polynomial? It is. It's written in factored form, but my exponents are all whole numbers, so it works. So for the degree, we are going to encounter problems like this a lot. They'll be written in factored form. And so we have to think about, if I multiply this all out, what would be my highest power of x? So if we think about it, I have an x cubed here. This would give me an x squared. So when I put it all together, x cubed times x squared would give me x to the 5th. So if I multiply this whole thing out, my highest power would be 5. We don't have to multiply it all out. We just have to think about what it would be. He said you guys would be good. All right, so far so good? All right, so here's what I want you to do. Take a second on your own. Draw me a rough graph of each of these. Doesn't have to be real precise. You can use your graphing calculator. I'm not really even looking for a lot of exact points. I really just want to talk about the shape. Okay, so figure out what shape each of these things would have. And draw a rough sketch for me. When you looked at x cubed and x to the 5th, what did you notice? They pretty much look the same. What's really the only difference? Can you tell? One was a little bit skinnier than the other. The x to the 5th was a little bit more skinny. X to the 4th, what did that one look a lot like? X squared. X to the 6th looks the same. What's the only difference? As that exponent goes up, what's happening to it? It's getting skinnier. Okay. So this leads us into what we call end behavior. And this is something we will look at every single time we graph a polynomial. So it turns out if you just have x to a power, if that power is even, it will look like x squared. And if that power is odd, it will look like the x cubed. The only difference, as the power gets bigger, the graph will narrow. So it just gets skinnier and skinnier, but the same general shape is kept. All right, so big thing, our end behavior. I put a big star next to this. This is what happens if you go forever in the positive or negative direction. If you look in the textbook on any of these. It gives some more wordy explanations. So it's going to say, like, as x approaches positive infinity, f of x approaches positive infinity. And I don't really think it's necessary to be quite that precise, so we're just going to draw arrows. You're just going to draw arrows going up or down and tell me which direction it's going. So it is solely determined by the leading term in a polynomial. That is the term with the highest exponent. So it turns out if we have even degree, think about the x squared, the x to the fourth, the x to the sixth, which direction are the ends going? They're both going up. So as long as your leading coefficient is positive, both ends would point up. Think about our quadratics. When we threw a negative in front, what happened? It flipped it. And so in that case, if the leading coefficient is negative, both ends will point down. So if our highest power is even, it's going to act like a quadratic. Either both ends pointing up or both ends pointing down. If our leading coefficient is odd, then it's going to act like a cube. So if you think about the cube, the left end is pointing down, and the right end is pointing up. So it's down, up. But what happens if you throw a negative in front? Flips it. And in that case, it would be up, down. So when I ask you for the end behavior, it's not anything, you're not going to have to do a big calculation. You are literally just looking at your polynomial, finding the leading term, and going from there. So let's practice that. A lot of times the leading term is the first one, not always, so just double check. This is my highest exponent. So it's odd, which tells me what? Now it looks like a regular cube function. The only thing that would change it is if I had a negative in front, but I don't. So my end behavior is down, up. This end's pointing down and that end is pointing up. What's my leading term? Okay. So at first look, that's an even power. So that tells me it's like a quadratic. What's the negative do? Flips it. So both ends are pointing down. Okay. When it's in factored form, we have to think a little bit more. I don't want you to take the time to multiply this whole thing out. Okay, we're just thinking if I did multiply it. We're looking at the leading term would be the highest power of x. So we have a 3, we have an x. This one would give me an x squared because of the square on the outside. So if you multiplied 3 times x squared, we get 3x cubed. That's just telling me what my leading term would be if I multiplied it all out. So, what's my end behavior? Down, up, because it's a normal, it's a cube. We don't have a negative in front, so always go left to right. Does everyone understand how I got that one? One more of these. Okay, there's a lot here. So let's think about if we multiply it out. I have a 1/2 in front. This one has an x squared. In this parenthesis, if you take an x squared cubed, what power would you get? In this we have an x to the 4th. So if I multiply that, x squared times x to the 6th times x to the 4th, we get x to the 12th. So even power tells me it's like a quadratic. I have a positive 1/2, so it doesn't flip. So my end behavior is up. Questions on how I got any of this? So we did some on the homework the day before yesterday where it gave you some requirements and you had to write a polynomial to go with them. So let's just find a polynomial for each of these. Degree of 3. What does the degree have to do with anything? Yeah, it tells you the shape of the graph. In terms of the zeros, it tells you how many zeros there are. So if the degree is 3, I should have 3 zeros, and that's exactly how many I gave you. If negative 3 is a 0, then what would be in my factored form? Okay, if 2 is a 0. If 5 is a 0. Okay. I didn't give you any other requirements this time. I didn't give you any multiplicity, so that's it. Right. B. Degree is 4. So I would expect 4 zeros. How many did I give you? 3. So what we can do is add a multiplicity to one of these. I didn't tell you which one, so there's several different polynomials that would work in this situation. If 0 is a 0, what do we put in our polynomial? Just an x, or x minus 0, or x plus 0. It's all the same. If 4 is a 0, that would be x minus 4. If 12 is a 0, that's x minus 12. But currently this would only be degree 3. So what's the easiest way to make it a 4? Just square one of them. It doesn't matter which one.
Can you get us passes for next hour? Like everyone who's in fire. There's a lot of us.
Okay.
Drawer locked.
Do you want me to just email him?
Well, he's not here.
He's not
He
here.
was up.
Okay. You guys send in the risers on here?
He brought them over already.
Okay, he
so
did.
they're in the hallway.
Okay.
Yeah, we'll figure it out. Yeah.
I don't think it's going to take as long because they got rid of a bunch of blue chairs.
We have to like get the chairs out of here.
We're not going to have enough, so we need to actually just which we need that. So I'm going to just talk with you guys if they can real quick and see if we need to do what we would pencils at least in a couple things, but probably not very much. All right, this one, degree of 3, so we need 3 zeros. Do we have all 3? Yep. Okay, if negative 1 is a 0, then we have to have, if 1 is a 0, okay, if 2 is a 0, all right, then I gave you this. The y-intercept is 1. That's kind of like a point on my graph. That's saying a y-intercept, what's my x value there? 0. So it's saying when x is 0, this whole thing has to equal 1. Remember the ones we were doing the other day where we had a number out in front? We need to figure out what that number is here. So if I plug in a 0 for all my x's, 0 plus 1 is 1, 0 minus 1 is negative 1, 0 minus 2 is negative 2. This whole thing has to equal 1. So this gives me 2a equals 1. So a is 1/2. So my polynomial has a 1/2 out in front. All right, so I could give you different aspects. I might give you, a degree or an intercept. You just have to make sure that your polynomial meets all those requirements. So far, so good? We're going to cover just a little bit more for today, and then we'll kind of wrap up. So I want to talk a little bit about terminology. So we've already said, in terms of a graph, zeros are your x-intercepts. It's where it hits the x-axis. So I might say that something is a 0. I could say that x equals that number is a solution to p of x equals 0. So if I said 2 is a 0, that means when you plug in 2, it equals 0. I could say x minus c is a factor. If 2 is a 0, then we put x minus 2 in our factored form. Or it's an x-intercept. So there's a lot of different ways I could say this, but I'm asking for the same thing every time. What you really need to know, the 0 is just a number. When I say the factor, what does it have to have with it? The x. So a factor is x minus something. A 0 is just the number. So we had some of these on last night's homework, finding the zeros. If it's already factored, you just have to tell me each piece. So does 5 ever equal 0? No. What makes x minus 2 equal 0? 2. What about x plus 3? And since it was squared, that's a multiplicity of 2. What about x minus 1/2? Multiplicity of 4. Multiplicities are going to be very important to a graph. You alright?
Yeah.
When I look at this one, if it's just an x out in front, what's your 0? If it's x plus 1, 3x minus 2. And x minus 5. So now let's figure out what the multiplicity does. We already kind of know. When I had you guys graphing to find, you had your list of possible zeros and you were looking at a graph to find one that works. Marker's dead. If I gave you a graph and it looked like this. So let's say we had a polynomial, it hit at a number and bounced. What did I tell you about your possible zeros? Yeah, at 2, where this graph bounced, it was going to be a 0 more than once, right? It's going to be a 0 twice. So, as it turns out, anytime the multiplicity is odd, your graph will go through the point. So whether the multiplicity is 1, 3, 5, 7, if it has an odd multiplicity, then what happens, my graph will hit there and then just keep going. But if the multiplicity is even, the graph will bounce at the point. So if the multiplicity is 2, 4, 6, 8, it's going to hit it, bounce off, and keep going. Okay, so when we start graphing these, I'm going to be asking you, is the graph going to bounce or go through? And that is completely relying on the multiplicity. Odd multiplicities go through and even multiplicities bounce. So the very last thing I'm mentioning today, I just want to talk about turning points, and then I am pretty well done. So a turning point is where the graph changes direction. On the slides that I just had, when I talk about it changing direction, I mean it switches from increasing to decreasing. How many times does that happen on this first graph? Here I was decreasing and I switched to increasing, And then kind of right here, I was increasing and I switched back to decreasing. It had 2 turning points. It changed direction twice. If I'm looking at this one, how many turning points does it have? Only 1. So a turning point is where you change direction between increasing and decreasing. And your turning points are related to your degree. So a polynomial of degree n has at most n minus 1 turning points. That sounds a little confusing. If my degree is 2, your number of turning points is 1 less than your degree. So if the degree is 2, we would have 1 turning point. If the degree is 3, we could have at most 2 turning points. If my degree is 7, I could have at most 6 turning points. Okay, you don't have to have that many. That's the most you could have. It works in reverse too. So if I said, if you knew the number of turning points, your degree has to be 1 higher than that. So if I gave you, let's say I drew this picture. First of all, can you tell me by looking at that, would it have an even or an odd degree? Even, because both ends are pointing the same direction. Is your leading coefficient positive or negative?
Negative.
Negative. How many zeros does this have? 2. If I asked you the degree, it would have to be at least degree what? So I have 1, 2, 3 turning points. So that means it has to be at least degree 4. It could be more because you're not guaranteed to have, you know, if you think about x cubed, does x cubed have any turning points? No, but this tells us a little bit something about our graph. All right, the last one is just not necessarily anything too earth-shattering. There's always a turning point between each pair of zeros. If you're going to hit the x-axis and come back and hit the x-axis again, you have to change direction, right? If you're going up and go through the x-axis, you have to come back down to hit it again. That's all it's telling us. So, what I want to do now, I have posted a handout on Classroom. Some of them are really short, like there's end behavior questions, and all I'm asking you to do on those is draw the arrows. There's some questions that says, how many turning points would this have? So it's just 1 less than the degree. And then at the end, there's some graphs and